Hey, this is Leach with Simpson Math, and in this video, we're going to look at solving equations using Gaussian elimination. That's where we're going to use matrices to help us solve our systems. So first, let's take a look at what in the world a matrix actually is. So you can think of a matrix as kind of just a mathematical table. We have rows, and then we have columns. And we start numbering these rows and columns starting in this top left-hand corner. So this 3, -2, 6, that's what we would call row 1. Row 2 would be 1, -1, and 5. Notice that we don't put anything in between our columns, so I'm not putting commas or dashes or anything like that. A dash would be considered a negative. So make sure that there's enough visual space between your rows, so that way it's nice and clear what's in what row. We have a notation for identifying each item in our matrix. So if I was to say row 1, column 1, what is in row 1, column 1? Well, that would be this 3. It is in the first row, and it is in the first column, so that's that 3. Well, what would be in row 2, column 3? Row 2 and column 3, so it's this 5. Now, matrices are going to be helpful for solving systems because I can kind of turn these numbers into a system. I could think of those 6 numbers as 2 equations. It could be like 3x minus 2y equals 6. Notice how that 3, the -2, those are the coefficients on the x and the y respectively. And then I have that 6. Now, later we'll talk about something called an augmented matrix. I'm just trying to get you an idea about how this is even applying to systems. And when we do, we often draw a vertical line right there to kind of represent those equal signs. That second row could just be like an x minus y equals 5. So if you're already starting with this understanding that we can simplify the way that we write our systems by basically just dropping the variables, dropping the equal signs, and just writing the numbers and in the structured order. Notice I have my x's and then y's and then numbers. You might start to be seeing how we can be manipulating these things called matrices to reach at our solution. So there are actually 3 special ways that we can manipulate these matrices. There are 3 matrix row operations. And when we're doing everything we're about to do in this lecture and the next, we have to keep in mind that we can only do these 3 procedures, these 3 operators. And just a little bit of just understanding. You'll see why it makes sense in a second, but our goal when we do Gaussian elimination is to get a 1 in the top left-hand corner. So when I'm working through these 3, introducing these 3 operators to you, that's kind of my goal, is to get a 1 in that top left-hand corner. So I'm starting with this introductory matrix that I showed you, that there was 2 rows and 3 columns. So one thing that I can do is I can just interchange the 2 rows. So just think about this. If I have the equations in the 2 that I showed you a second ago, that 3x minus 2y equals 6, and that one below it, there's nothing special about which one I write first and which one I write second, right? I could just change them, right? Just simply change their order. That doesn't change the solution. That if I was graphing those lines don't change positions. Their intersection doesn't change around at all. So that's a very valid maneuver, is just to swap them. So I could do just that. If I'm wanting to get a 1 in this top left-hand corner, I could literally just swap them around. And so I've kind of color-coded this for you just to help you see that. So blue goes to the bottom, red goes to the top. And so now we have this 1 in the top left-hand corner. So when we do this, we have a notation for this to show your work. We're communicating that this is row 1 and this is row 2, and that we are interchanging their locations, so they are swapping places. All right, so that's our first one, is to interchange 2 rows. All right, next is that we can multiply a row by a scalar. We did this when we were doing elimination method. We would take an entire equation and multiply by a constant, so that way when we added, we would eliminate a variable. Well, we're just going to do that same thing here. I'm just going to multiply the entire row. Instead of calling it an equation, we're calling it a row. We're going to multiply the entire row by a constant, so that way I can achieve what I'm wanting to achieve, my various goals. And one of my first various goals, again, is to get this 1 in the top left-hand corner. So what can I multiply by this 3 to make that 3 be a 1? Well, I can multiply by 1/3. So I can multiply this entire row by 1/3. And so 3 times 1/3 is 1. 2 times 1/3 is a negative 2/3. 6 times 1/3 is 2. Multiplying times 1/3 is the same thing as dividing by 3. So basically distribute this 1/3 into all three parts, and this is our notation. We take what we call the scalar. It's the value that is scaling. It is just a constant. It is a fixed number. So we're going to multiply our scalar times our row, and then we're going to produce our new row 1. This n, it's not quite a standard notation. You might not see it if you're looking for help in other books or websites, but we're using this n to represent new row 1, right? And this right here, you'll see later, actually, and above my head, there's an SRA. So the S is our scalar, and this n is just representing new. So what I'm doing is, notice I am replacing the old row 1 with the new row 1. So you don't see this row anywhere anymore. It's been replaced by 1/3 R1. All right, in our third procedure, it's going to pick up kind of that idea of producing that scalar, but then we're going to be adding it to another row. You can essentially think of this as what we did when we did the elimination technique. I would multiply and then add to produce zeros in certain locations. But here, my goal again is I want to try to get a 1 in the top left-hand corner. So if I want to force this to be a 1, yes, I know it would be much easier just to swap the two rows. This is just understanding this technique, this operation. So I'm going to multiply this bottom row times -2 and add it to the top row. So let's look at that. I'm going to take row 2 and multiply times -2. So let's distribute that -2. 1 times -2 is -2. -1 times -2 is +2. And 5 times -2 is -10. So that's me scaling R2 by -2, which is basically what I did in the previous row, in the previous operation. But now I'm going to add it to row 1. So I'm going to add it to this top row and then replace that top row with my new row. So I'm going to make a new R1. So I've just copied down my row 1, and then I'm just going to add. -2 plus 3 is 1. 2 plus the -2 is 0. And -10 plus 6 is -4. So now I have this new row 1, which is 1, 0, -4. I'm going to replace my row 1 with this new row 1, 1, 0, -4. So notice that R2 did not change. So yes, in my side work, when I did my math right here, my R2 changed, but that was in my side work. I did not replace anything with that directly. If I did, it would be doing this second concept, that multiplying the row by a scalar and just being done with it. But if I'm going to add it to something else, then I need to, I'm doing this on this outside here, and then I'm replacing that new row 1, that row 1 with new row 1. All right, so you're like, okay, cool. Well, here's a summary, and these summaries are also written above my head, and they will be there throughout the video. And then our goal when working with Gaussian elimination is to get what I call ones on the main diagonal. So if you think about this diagonal, remember we start matrices up here in this top corner. Along the diagonal, right there, this would be the R1, column 1, R2, column 2, R3, column 3. All right, so it's when the numbers of the row and the columns are the same. So along ones on the main diagonal, and then beneath those ones, we have zeros. So and these little stars that you see here, those stars are just representing, they can be any numbers, I'm not worrying about them. So Gaussian elimination is complete when I have ones on the main diagonal and zeros beneath them. Now, working this is a little bit kind of like working a Rubik's Cube. If you've ever played with a Rubik's Cube, it's pretty easy to get one side, one face the same colors. But then you start trying to work on some of the other sides or the other things, then all of a sudden you start messing up that other side. Like, I can't move that because then my other color will get messed up. So, but people have figured out Rubik's Cubes that there's a nice little trick and ways to maneuver, kind of like with this. The recommended work order, though you can deviate from this. The recommended work order is to get this one first, so this is our first task, and then second, get that 0, third, get that 0. The general idea is I'm going to get this one and then use that one to make them be zeros beneath. Then we move up and we get this this one here, that's our fourth position. Use that one to get the 0 beneath. And then lastly, we get this last one. So the general flow is get a 1 in the top corner, use it to get zeros beneath. On the next one down on the diagonal, get that one, use it to get zeros beneath. The next one down on the diagonal, get that one, zeros beneath. If this matrix went on and if this was much bigger, which we won't see this, but if it was much bigger, you just follow that pattern. Get a 1, zeros beneath. Get the next one, zeros beneath. Get the next one, zeros beneath. On and on and on. Like I said, you can deviate from that pattern, and sometimes as you do them, you might accidentally kind of do 2 at once. But this should always work for you. And then just to be clear about these steps, it might take a few of these row operators, the interchanging, the multiplying times the scalar, or multiplying a row and adding, to achieve at this one. Some students get confused because they think that there's just one magic bullet, one silver bullet that will just make this suddenly become 1. No, it might take some finagling. And then once I get that, it might take a little bit of finagling to get the other things. And you'll see the ones are the ones when you have to be the most creative. So let's take a look at this first example. So I have this system of equations, and we're going to solve this using matrices. So first, I need to get it into a matrix. So if I just wrote down the coefficients, so the coefficient of this first x is just 1, coefficient of the y is 1, the z is 2, and that is 11. So I'm going to do just that. I have 1, 1, 2, 11. And then we use this kind of vertical line to represent the equals signs, just to kind of keep the two sides separate. All right, and then I have a 1, 1, 3, then my equals and 14. So 1, 1, 3, 14. Again, notice there's nice, good, clear vertical space between each of these. It's not crowding. These ones don't suddenly look like 11. They're separate from each other. And then on our third row, 1, 2, -1, 5. So 1, 2, -1, 5. Make sure that this step you don't mess up. You'll see that everything within this matrix builds on itself. If I mess up right here, later I'll use that number and it's just going to compound on itself. So you have to be careful on every single step. And that begins in the very first step. Check all of your signs, check your numbers. Again, whenever I write down my things, I'll write them down and then I'll do a quick check. I'll just look for my signs, make sure my signs are right, and I'll look through any numbers, make sure I'll just double, triple check that I've written it down correctly. All right, so let's work through our pattern. So my first goal is to get a 1 in that top left corner. Oh, look, success. I did it. I worked real hard and I got a 1 in the top left corner. Now, it's not always going to be that simple, but hey, job well done. Pat yourself on the back. We got a 1 in the top left corner. Now, we need to use this 1 to make these others be 0. All right, so typically when we're going to be using that 1 to make the other 0, we're going to be using that third technique. Multiply row by scalar, and then add it to another row. So I notice that this entire column is 1s, but I'm really just focusing right now on just 1 and 2. So I noticed that if I was to somehow make this if I could make that be a -1 and add -1 to that 1, I would then have a 0. So I can do just that. I'm going to multiply this entire row 1, so all row 1 is going to get multiplied by a negative, and then I'll add it to row 2, and that will become my new row 2. So I'm going to, basically when you multiply by -1, you just change your signs. So change my signs on all of them. Yep, change my signs. Again, double check, write it down, and then do a quick double check. And then now let's add. -1 plus 1 is 0. -1 plus 1 again is 0. -2 plus 3 is +1. And -11 plus 14 is a +3. It doesn't hurt to double check that. And remember, this is my new row 2. So I am replacing my row 2 with 0, 0, 1, 3. Right? If you look, if you look at the top row and the third row are the same as what we have up here. All right? The only thing that's changed is row 2. And notice, I've met my goal. Right? My goal was to get, oops, I erased. My goal was to get that to be a 0, and I've done that. All right, so now, again, I said 0's below. This is steps 2 and 3, so I need to make this one now be a 0. And I'm going to do it using the same set of skills. So I'm going to multiply this top row by -1. So there it is. And now I'm going to add it to row 3, and then I'll get a new row 3. -1 plus 1 is 0. -1 plus 2 is +1. -2 plus -1 is -3. And -11 plus 5 is -6. So my new row 3, I'm going to replace row 3 with 0, 1, -3, -6. All right? So I've achieved my first 3 goals. I have 1 in the top left corner and 0's beneath it. All right, my next job is to move on and make row 2, column 2, R2C2, R2D2's friend, 0. So looking here, I see, well, there's this one, but if I move this row down, I'm now moving this row with this one with it. So I need to make sure that whatever adjustments I do does not change those 3 values. All right? So I have to be careful. The general advice is probably leave this top row alone. Because if I was to move this, well, now I'm moving this 1 down. If I was to do the third method, multiply and add, if I was to multiply this row by something and add it, I'm multiplying this 1 and then adding, and now I'm changing this. So it's best to probably look below for some help. So when I look down, I see, well, there's a 1 right here and a 0. So if I just swapped these 2 rows, well, then I'll have a 1 right there where I'm wanting it. And bonus, I'll have a 0 also where I want it. So let's do just that. So I'm just going to interchange row 2 and row 3. That's that proper notation. Interchange row 2 and row 3. So I have this here. So all I've done is I've just swapped them. One quick note about notation. If I was to name these rows right now, after I've done step 4 is completed, and I'm just blindly looking at this matrix, and someone was to ask me, where's row 2? Well, there's row 1, here's row 2, and here's row 3. I don't care that what is row 2 now was row 3 in the previous step. Don't care. The reason why we have this is for consistency. Because if in some future steps I need to refer to row 3, I don't want to have a memory that where row 3 was 5 steps ago. It's just where's row 3 now in this one step. I execute it, and then I move on. And then now, if I refer to row 3, I'll be talking about whatever that new row 3 is. So just to be clear about that notation. All right, so now my goal was to make that be a 1. And oh, look, it is. Yay me. My next step is to use R2C2 to make 0's below. So use this to make 0's be beneath it. Lucky stars, it's already a 1. All right, yay me. Now I need to move on and make R3, row 3, column 3 be a 1. By luck, it also already is. So I've actually already completed Gaussian elimination. So when you have 1s on the main diagonal and 0's beneath it, you completed Gaussian elimination. Now, just a note, in our next lecture, we'll pick up at this same very step with this same example and finish within the matrix, and that process is called Gauss-Jordan. That complete process is called Gauss-Jordan. When we finish, and actually we'll make these be 0. A little bit of spoiler. But today, once we have completed Gaussian elimination, we have 1s on the main diagonal, 0s beneath, we're then going to exit the matrix and finish algebraically. So let's rewrite this as a system. So remember how this started, way up here. I started with this system, and we looked at the coefficients, and we turned it into this augmented matrix. I'm just going to undo that. Right? We've done all legal maneuvers, changing this matrix around. So now I can just rewrite this as equations. So let's start in this bottom row. Notice this is my x column, y column, z column, and then the number column, basically that constant column. So when I look at this, this is 0x plus 0y, so 0, plus 1z equals 3. This is the big deal. This right here, that one row, I'm jumping straight to it. This is a big deal. I just found that z equals 3. So right here, this is z equals 3. This is a big, huge deal. So I'm going to be able to use this z equals 3 to be able to back substitute and find all my other values. So let's get this orange equation. This is 0x plus 1y minus 3z equals a negative 6. So that plus 0x, don't have to write that. There's the y minus 3z equals negative 6. And then my 1x, 1y, 2z, and it equals 11. And again, notice 2z, that's why I cross my z's, because sometimes my 2's can look like z's, so you don't want it to look like zz or 22. So now that we've gotten z equals 3, and this is the big deal. This is when you do Gaussian elimination, that bottom row is always going to be z equals number. So I can take that z and back substitute. So I can take this z and plug it into that z right there, in that previous equation, or in row 2's equation. So I now have y equals, rewind. I now have y minus 3 times 3 equals negative 6. So that's y minus 9 equals negative 6. Add the 9 to the other side, and y is 3. So now I have that z is 3 and y is 3. I can then back sub and plug the, point up here, plug the z into here and plug the y into there. And so then I'm going to have x plus 3 plus 2 times 3 equals 11 with that substitution. And then we simplify. We multiply, we get 6, add the 3 with that 6, and we get 9. Subtract the 9 from both sides, and x is 2. So we can then write this as an ordered triple, because we have three variables, x, comma, y, comma, z, and then again put it in that set notation, because it's the set of it's our solution set, though there's just one thing in that solution set. All right, so there you have it. That is how we that's how we perform Gaussian elimination. All right, we're going to do another example to try to help us set it in stone. But remember our goal. We want 1's on the main diagonal, 1's in the main diagonal, 0's beneath, and we work basically in that order. We get the 1, use that to make 0's beneath. Get the next one, use it to make 0's, get the last one. All right, let's take a look at this one. If you want to go ahead and dive in, pause the video and move on, be my guest. I'm just going to do this step by step by step, but I'm just keeping things covered in case in case you get stuck at moments and you don't want to be spoiled by what's next. All right, so let's write as an augmented matrix. All right, so let's do that. All right, when I write it as an augmented matrix, all I do is just basically you can more or less erase the variables. If it's a 1, make sure you have the 1 still there, or a negative 1. And then this was equals to 0, so it's still 0. 0 is a number. If for some reason, let's say that minus z wasn't even there at all, it was just 3x plus y equals 0, well then this would just be a 0 here. All right, so if you don't see the variable, then obviously the coefficient is also 0. So there's my augmented matrix. Make sure to always put your brackets on either side. You might see there's various ways you can do brackets. I always do them as square. Some people do them as giant parentheses. Some people just do them as straight lines. You can really do it either way. I'll tend to do this square brackets. And then I would like to have this line in the middle. If you want to be extra fancy, you can make it be a dotted line. I've seen that as well. I'm okay with that, but I do want some sort of barrier between my coefficients and my constant. All right, so my first goal is to make R1, C1 a 0. So this top left corner, I need that to be, oh, misspoke. Top left corner, I need that to be a 1. I'm looking right at it and I said 0. So I need this to be a 1. In my opinion, take the path of least resistance. Sure, I could multiply this by 1/3, but then look what kind of fractions you're creating. What do you see? What's the path of least resistance? I can swap rows. I can multiply by a scalar, but if I just multiply this at 1/3, I could multiply this by a negative and add that up. That could work. That's one option. But isn't it easiest just to probably swap those two? I just swap row 1 and row 2. All of a sudden, don't I have a 1 in the top left corner? Yep. Now let's do just that. So I just swapped row 1 and row 2. So do you see how there's multiple ways that we can work to do the same problem or the same step? Some are just easier than others. And then this path, when I just swap these two, might lead to maybe a more complicated step later, just because of the way the numbers work out. And maybe doing like multiplying by negative here and adding it up there might make the numbers be a little bit easier in some later steps. There's lots of different ways to do this, but as long as you're doing something legal, you're not doing something wrong. All right, so our next one is we're going to use, and I really like saying that word use. We're using this 1 in the top left corner to make the others be 0. Use that 1. And so typically it's always going to be this third operation, which is going to make the other rows, this 3 and this 2 be 0. So I'm going to multiply. I can multiply this top row by -3 and then add it, and that will force that to be a 3. Force that -3 plus 3 to be 0. And I can do the same thing with that 2. So let's look first here. All right, so let's multiply -3 times row 1. So -3 times 1 is -3. -3 times 1 is -3. -3 times 2 is -6. And -3 times 6 is -18. Now for my double check, this is what I like to do. One, always make sure you double check. It's very important. Most common mistake that students will make is they'll just be careless in just a little spot. They'll forget a sign, or they're just multiply just slightly wrong. So I like to break apart the positive and negative aspect and then the numbers. So I'm just going to check. I'm multiplying times a negative, so that means all the signs need to change in this top row. They are all positive, so they now all need to be negative. Yep, good, did that. Now, let me just triple the numbers. 1 tripled is 3, 1 tripled is 3, 2 tripled is 6, 6 tripled is 18. Good. So that's how I like to handle my double check. I separate the negative aspects and then the actual number. All right, copy this down. Make sure when you copy it that you write it correctly. 3, 1, negative, yep, and 0. All right, so let's add. -3 plus 3 is 0, which is what I'm looking for. -3 plus 1 is -2. That's -7, and that's -18. And then remember, this is my new row 2, so I'm replacing row 2 with this new row. Now, optionally, you can do both of these at the same time. So over here, I'm taking care of row 3 at the same time that I'm taking care of row 2. So I'm multiplying the top row by -2, so that way when I add these together, I get a 0 here in this spot. So I'm going to distribute my -2. So now I have -2, -2, -4, -12. I can double check with the signs and the numbers. And then we add, and we get those cancel to 0. Those also cancel to 0. -4 plus 3 is -1. -12 plus 10 is -2. And put them in their place. And now it's my new row 3. It is replacing row 3. All right, good. This is looking good here. So I'm noticing a few things. This is happy. Even though it's not my next goal, I notice that I have a 0 right there. I also notice that that's almost a 1, so that's a pretty easy switch. If you want to go ahead and probably even take care of that, you could, but my next goal, though, in order, is to take care of that -2. So step 4 is to make row 2, column 2 into a 1. Sounded about work, me writing down these steps, that's optional, that's for your notes. Me doing this work, that is not optional. Me denoting that I'm interchanging row 1 and row 2, that is not optional. So the steps, I'm not needing. My clarification about what I'm doing is absolutely required. All right, and also notice that I'm working vertically. I'm not putting this to the side. It just take up paper. It'll be fine. All right, so now I need to make row 2, column 2 into a 1. You think about the best way to do this. So I'm looking at my list of operators above my head. I could just swap. So there's a 1 here that I could swap, but that is not going to achieve, that's not going to make anything nice, because now all of a sudden that becomes a 1, this becomes a 0. That's a big headache. Nope. I could multiply by scalar. I could also multiply by something and add. These 1s are when you're going to have to be the most creative. Since this thing is already a 0, I can't really use anything here to influence that. So really, I'm stuck with multiplying by a scalar, which means I'm going to see a fraction for a little bit. So I'm going to multiply this second row times a -1/2. Let's see that. So yeah, I have this note right here. Boxed it in pink, it's so important. We can always make a 1 by multiplying by the reciprocal. So the reciprocal of -2, just flip it over, is a -1/2. The sign does not change on the reciprocal. -2 becomes -1/2. So if I multiply -1/2 times R2, so let's just distribute 0 times -1/2, 0. -2 times -1/2, 2's reduce, negative times a negative is a positive, and so we have a +1. If I do -7 times -1/2, the negative times negative is positive, but 7 times a half is 7/2. And multiplying by a half is the same thing as dividing by 2. So you can just think 18 divided by 2, that's 9. Negative times a negative is a positive, so then we have a 9 there. So my new row 2 is now 0, 1, 7/2, and 9. Right? So my next goal is to create zeros below this. So zeros below this, below my 1. I could, like we mentioned earlier, I saw that it was already a 0 there as long as I could keep it. I kept that a 0 because sometimes you might see the 0 in a spot that's optimal, but then things are going to move around and it won't stay that way. So here when I move that, to do this step, it's already a 0. That's good. So let's move on to making this last one be a 1. Well, it's already a -1, so what could I do to make that be a +1? Yeah, I hear what you're saying. I can multiply that entire bottom row 3 times -1, right? Again, just one more plea about notation. Please resist the urge of trying to communicate math like this. That is not how we communicate matrix math. It's just bad grammar, basically. So make sure that we're communicating in the same way. So I'm going to multiply -1 times R3, and I get my new R3, which will then just basically switch those signs. So 0, 0, -1, -2 is now 0, 0, 1, 2. Right? And notice, I have a big celebratory Gaussian elimination complete. Huzzah! All right, we have 1s on the main diagonal, 0s beneath them. So my Gaussian elimination is complete. Again, in the next lecture video, I'm going to be picking up where we left off right here, and then completing the process called Gauss-Jordan elimination. But now we can just solve this by back substitution. So let me write down my system of equations. This tells me right here that z equals 2. So z is 2. And then I have y plus 7/2 z equals 9. And then x plus y plus 2z equals 6. You don't have to work backwards like that, but I like just looking right here and be like, ah, z is 2. That's my next thing I'm going to do is plug in. So let's do just that. I'm going to plug in this z equals -2 into the z, get the y, and then backsub both of those into that y and z. Alright, so I backsub and I got that y is 2. Don't stress too much. I'm going to be giving you nice integer solutions most likely because I'm not a mean guy. So notice that this 2 and that 2 reduce to 1 and we're left with just 7. So fear not the fractions. And then subtract the 2 from both sides. Sorry, subtract the 7 from both sides. I had 2 in my brain, and we get 9 minus 7 is 2. And we backsub, so we take our z is 2 and our y is 2 and plug them in. And then we end up with x is 0. It's fine that x equals 0. 0 is a number. We don't discriminate against zeros. It's just a number as well. So that's 0, 2, 2. So x is 0, y is 2, z is 2 in our order triple in our set notation. Well, there you have it, folks. That's how we do Gaussian elimination. I hope this helps you understand Gaussian elimination a little bit more so that way you can be successful on your homework in this course. Take care and see me in the next video when we'll talk about Gauss-Jordan elimination.